Okay, we're continuing on. Pretty much finished. I think 12, if I'm not mistaken. Maybe one more thing we're going to talk about before we move on to 14, which again is the next organic chapter. We will come back to 13, which is carbohydrates after the organic chapter. So last time we got into, I think, aldehydes. And remember, aldehydes have a functional group of carbon, oxygen, double bond, that carbonyl carbon, which is that polar group, kind of positive, negative there. And that is our functional group there for our aldehydes. We also talked about ketones, which have basically a 3-carbon run there with the carbonyl carbon, the carbon oxygen double bond there in the center of those 3 carbons in a row. To name aldehydes, we basically just put an AL at the end of the longest alkane name. If we had something like this, that is 3 carbons, which is based off of propane. This would then be propanal, AL. A reminder that with aldehydes, because it has the hydrogen on the functional group, that functional group has to be at the very end. So we don't need to give the location of where that carbon oxygen double bond is located. It should really be at one side or the other of the longest carbon chain. But for numbering purposes, it is always going to be number 1. And in this case, we would have a chlorine there at number 2. So this would be something like 2-chloral propanal. Coming to our ketone, again, same idea here. And I'll go here, here. Yeah, maybe we'll put a chlorine over here as well. And something like that, maybe. Once again, the longest carbon chain here going to be straight across, and that is 1, 2, 3, 4, 5. That is pentanone, O-N-E, like a ketone. Remember, once you get to kind of like that 5-ish or more carbons, you do have to get the location of where that carbon oxygen double bond is located. And we do want to give it the priority in terms of smallest number. And obviously going in this direction, we'll put it at carbon number 2. So 2-pentanone means that's where our carbon oxygen double bond is located. And because we have to kind of lock in the numbering on that direction, that would obviously dictate where our chlorine would end up as a 5-chloral 2-pentanone pentanone in this case. We talked about obviously how to make both of these and some reactions that they undergo. We obviously make a aldehyde from a primary alcohol, as we talked about there, and that is made through the oxidation of a primary alcohol. So that's primary alcohol there. And oxidation. And obviously that's going to be our loss of our hydrogen there off of the carbon and the oxygen, making it a double bond as we go that way. Remember, you can get back your alcohol by doing basically the reduction in that direction. As we also talked about, we can further oxidize a aldehyde to a carboxylic acid. And again, this is sort of adding oxygen in to make a carboxylic acid here. So we could kind of go to a carboxylic acid by oxidizing that one more time in this case. Obviously here, secondary alcohol is how we get to our ketone. And again, if we oxidize this secondary alcohol, again, taking out our hydrogens and making a double bond in there, we're going to get to our ketone in this case, along with the hydrogen that comes off. And again, we can do a reduction to go back the other way as well. So again, that is how we make both of these. And we talked about the reduction reaction, which again is basically just breaking this double bond, kind of like what we do with carbon-carbon double bonds to make single bonds, and adding in the two hydrogens across that will go in the opposite direction there. Any questions on those two there? Remember, we will not continue to oxidize that any further, so you'll kind of stop at the ketone. We also talked about Benedict's reagent and also Toland's reagents, which are two reagents that are used to get a positive sort of test as you kind of go from an aldehyde to a carboxylic acid. Again, when the carboxylic acid gets oxidized, the copper there in the Benedict's reagent gets reduced and kind of goes from a bluish color to a reddish orangey type of color as a positive test. Any questions on that there? Okay, so last two things we're going to talk about in terms of chapter 12 are two more types of reactions that both aldehydes and ketones can undergo. And so let's talk about those before we jump into chapter 14. And if we took an aldehyde, doesn't really matter what type of aldehyde, we'll just make it maybe a 3-carbon one here. And we'll do something like this. And if we add an alcohol to it, so if we take basically an aldehyde and we add an alcohol to it, we will get a reaction that will happen. And this reaction is pretty identical in a sense to how we add like the hydrogens back to this. It's all going to happen in this location. So everything's going to happen right there at kind of our functional carbonyl group there. And just like when we add, for example, something like hydrogens back, we can't do it without making that double bond into a single bond. The same thing is going to have to happen here to make room for it. And this alcohol is actually going to add in kind of two parts. We will add a hydrogen, and then we will actually add the other part of the alcohol, which is this oxygen carbon group. Maybe not the best choice there for highlighting. Try a different color, maybe. Green, maybe. And we're going to add this guy here. So that is how the alcohol is going to add. And what we're really adding in this sense is a hydrogen that is positive, and this oxygen carbon group is actually quite negative. And so these are kind of the two things we're going to kind of add in there. So when we do this, once again, nothing much changes other than we need to make room for it. So just like normal, we're just going to make that double bond actually into a single bond. Now, when we talk about this carbon-oxygen double bond, as I mentioned before, it is a polar bond where the carbon is more positive, the oxygen is more negative, and this is going to kind of help determine where things are going to go because opposites are attracted to each other, right? So the positive hydrogen will end up over here at the negative oxygen part, and the negative oxygen carbon guy will end up over here at the carbon. And what that's going to make is a hydrogen here, and this oxygen carbon group gets added here, and that's basically from the alcohol. So again, our two parts there, if we don't get rid of the screen, gonna put that guy there, and our hydrogen right there. That's where they're going to end up. And this sort of compound that we just made actually has a special name, and we'll see it again when we talk about carbohydrates and such. This is what is known as a hemiacetal. And a hemiacetal is the type of compound it is not like the specific name for it or anything like that, but it's the type of compound it is. And what a hemiacetal has is basically three characteristics. It has an OH group, so it has this OH group. It has this oxygen carbon group, and it has a hydrogen. And that's kind of the main components of a hemiacetal, is it will have those three sort of components. Now, if you just add one alcohol to the aldehyde, that's pretty much where you'll end up. You'll just end up at the hemiacetal. But you can add a second alcohol to this aldehyde. And if you did two alcohols, what would happen is we would actually get this hemiacetal continuing to react with the second alcohol. And if we just kind of recopy what we just had there. And if we add, again, same alcohol, different alcohol, it doesn't so much matter here. And what's going to happen in this case is sort of going to add a similar way. We're going to have this part of it, and we're going to have, obviously, the hydrogen part in this case. I'll make that yellow. And it's going to kind of happen in a double step here. And really how it sort of happens is not super important for us or anything like that. But essentially what's the first thing that's going to happen here is this hydrogen will go and basically find that OH and will make water. And when it does so, can give you an OH kind of plus here. And what's going to happen is, I'll just put a little bracket around this, sort of the intermediate step. This guy will actually just come off, basically. So that guy will basically come off when it does so. And that's going to result in water happening, obviously. And in this case, I'll just draw it underneath. This guy will now, once he loses that, this guy will now become very positive, and that's really good for our negative oxygen carbon group there. And this guy, which is again basically this, is going to be really attracted and basically end up right there. So basically what's going to happen is the OH group and the oxygen carbon group are just going to swap places basically. And we will end up with two oxygen carbon groups on that same carbon. And this guy is what is known as an acetal, basically. So that is an acetal. So if you add one alcohol to an aldehyde, you get what is known as a hemiacetal. It's kind of an intermediate. And if you add a second alcohol to it, you'll go all the way to an acetal. And the difference is the acetal has two oxygen carbon groups. And that is these two groups here. They both come from the alcohol. And it still has a hydrogen, basically, and a hydrogen on it. So those are the two there. And again, we will see some hemiacetal formation with carbohydrates a little bit later on. And it's sort of an important little functional sort of group that occurs in this type of reaction. Any questions on those there? Yeah. To which one? I'm sorry. Here? You can do it either way. If you want to put them on there, it's fine. Yeah, you could do that. There really is there's a bond like that. If that's what you're asking, you could do that. Or you could just leave it as OCH3. That's good. Yeah, that's good. Other questions? Okay. Now, this is basically what happens with an aldehyde. A ketone pretty much works the same way. You'll get that kind of intermediate if you add one alcohol, and you'll kind of go all the way to the end there if you add two alcohols. So just to show you what a ketone kind of looks like with this. And again, it's pretty identical to what just happened with our aldehyde. Again, if you take one alcohol, doesn't matter really what type of alcohol it is. It has to be like a one carbon alcohol. And again, the first thing that's going to happen here is we're going to break this double bond. We're going to add our hydrogen to the top. And then this guy, just like we did with the aldehyde, basically over there, just going to go in opposite places. And nothing else is going to change. Except obviously we need to make some room for that. And in this case, it's actually a two carbon group on that alcohol. So we'll get two carbons on there. And we'll just have one more here. And what we make here is in some books, they will still call this a hemiacetal, and some books will call this a hemiketal because it comes from a ketone rather than an aldehyde. So sometimes you'll see it both ways. I think nowadays people just kind of roll with hemiacetal for it as well. And what the difference here is, hemiacetal or hemiketal really will have an OH group, will have that oxygen carbon group that comes from the alcohol, and it will not have a hydrogen. So again, because this originated as a ketone, it doesn't have that hydrogen on that carbon, so it won't have that sort of hydrogen there in a hemiketal. So I'd say most people still probably call it a hemiketal. And again, it's basically this H from the alcohol and this oxygen carbon part from the alcohol basically goes there. So it's very similar to how we add the two hydrogens. We just break the double bond and put one part up on top and one part on the other. And if you added, again, two alcohols to this, the exact same thing is going to happen as what happened with the aldehyde. This guy is basically going to go off, and he's going to make water with this guy. So these two guys will come together to make water. And then basically we're just going to put what's left of the alcohol in that spot. They're just going to pop that guy right into that spot is basically where it's going to go when that comes off. And we will end up with this, which is what is known as a ketal in this case. And a ketal is like an acetal, but again, it derives from a ketone, which is why it's called a ketal. This has, just like the other one, two oxygen carbon groups and no hydrogen, basically. So that is the difference. And that's really how you can determine, for example, if you see one of these sort of groups, you can determine if you started with really a aldehyde or a ketone, is whether or not it has that hydrogen there. And if it doesn't have the hydrogen, then it definitely was a ketone you started with. And if you started with an aldehyde, then you would have that hydrogen still hanging out. So these are two reactions that can occur, one from an aldehyde and an alcohol, and one with a ketone and alcohol. Again, one alcohol kind of stops you in the middle. So a good way to remember it is something that's called hemi should probably have an OH group on it. Yeah, so we'll have the OH group on it. And again, if you had two alcohols, you'll go all the way to the end and you won't have any OH groups. You'll just have two oxygen carbon groups. Any questions on those reactions there? Yeah. Correct. So on an alcohol, right, that this OH group, which makes it an alcohol, right? This is a polar group, so the oxygen is more negative, the hydrogen is more positive. And so when this comes off, it comes off early as H plus, and it leaves whatever's on the back end of it as being kind of negative, still left over. Other questions? Okay. All right, that wraps up chapter 12. Off to chapter 14, our final organic groups. We're going to talk about carboxylic acid. We're going to talk about esters, amines, and amides. So we'll get into some nitrogen containing groups here. To finish up, like I said before, I'm not sure why she skipped 13 and went to 14 with this and then back, but we'll go back to 13, which carbohydrates, afterwards. All right, so let's start with carboxylic acids, and we saw the formation of a carboxylic acid, and the functional group for a carboxylic acid is this right here. This is our functional group. And a lot of times, sort of in formulas, you'll see this group written like COOH. So if you kind of see like a COOH written in a formula, it is basically the carboxylic acid group That is sort of the shorthand for carboxylic acids. Kind of like sometimes you'll see CHO written for the shorthand for aldehydes, but this is probably more common to see. Now, the carboxylic acids, again, have a very polar functional group. It has the carbonyl group, as we just talked about, which is partially positive, partially negative, but it also contains this OH group, as we just talked about, which also has a charge. So it's got two really kind of polar parts to this functional group, which is really important. And that gives it some properties that, for example, as we'll talk about, carboxylic acids could essentially is one of the few things that can beat alcohols in terms of boiling points and melting points, because when you get carboxylic acids together with itself, there is a lot of hydrogen bonding that can happen between those guys. And for example, here again, negative, positive, positive, negative, positive, negative, positive, and negative. So we definitely can have some hydrogen bonding happening here. We definitely could have some hydrogen bonding happening over here. So it creates a lot of really strong bonds between different carboxylic acids. And because of that, that allows them to be held together really tightly, and they typically have very high boiling points and melting points. So they're probably at the top of the organic list in terms of boiling points and melting points, because of those two functional groups being able to hydrogen bond with each other pretty easily. Um, so we kind of name carboxylic acids as oic acids, and that's sort of how we end the name. So as you can see here, CH3, C double bond OOH, that is 2 carbons based off of ethane. And if you just kind of drop the E off of it and put oic acid at the end, it becomes ethanoic acid. That's also, by the way, acetic acid, and major component of vinegar. We also see it in sort of line structure here. We got 1, 2, and 3 carbons, which is based off of propane, and that becomes propanoic acid. A reminder again, we do need to write in the OH here at the end of this line, otherwise it is just a carbon. And off of a benzene ring, you actually see it sort of by itself, kind of hanging off of the benzene ring, and that will be known as benzoic acid. So go back to your basic alkanes, drop the E, put oic acid, and you'll see it. In addition, just like the aldehydes, because this functional group does have the H on it, it will be at the end of the longest carbon chain. So it should always find itself either at one end or the other. It cannot be in the middle, otherwise that hydrogen will have too many bonds to it. So here is methanoic acid, again, because it has 1 carbon based off of methane. OIC acid, again, 2 carbons here, as we just saw there, based off of ethane, ethanoic acid. You do not need to give the location of where the carbon-oxygen double bond is or that functional group, because again, it should be at the end of the molecule, either one side or the other. But just like we kind of do with aldehydes, it will definitely be carbon number 1 if you need a number for other groups that may be attached. So although we don't give this guy's location, this is always going to be carbon number 1 in terms of numbering the longest carbon chain. So here again, we can see if we count it, we got longest carbon chain, 1, 2, 3, 4. Could actually get it going up as well if you wanted to. 4 is going to be based off of butane, so that's going to be butanoic acid. Once again, we don't need to give the location, but that will be carbon 1, 2, and 3 for our methyl group, and that'll be 3-methyl butanoic acid. Here, same deal. We got a benzene ring here, all the way around with our double bonds. And again, you will see this carboxylic acid group hanging off of the ring. And where that is attached to the ring would be carbon number 1. So wherever that is attached on the benzene ring, it will definitely be carbon number 1. And then because it is a benzene ring, you could go left or right. It really doesn't matter. And whichever way is going to give the groups the smaller numbers. So this is going to be 2 and 3 on this side. And again, that is how we get to our 2,3 dichloral, because there's 2 of them in this thing, benzoic acid. Any questions on that name there? Now, there are some common names that are sometimes used. We will again go by the IUPAC way of naming, but I would say probably these 2 names you might see a lot. Definitely acetic acid you see a lot, and again, that's the major component of vinegar for ethanoic acid. Formic acid, based off of formate here, which is our methanoic acid, but we will go by here. But I probably be a little familiar with these 2 because definitely things like acetic acid is used a lot in terms of naming it as well. But definitely probably should go ethanoic acid for acid name. Question. Yeah. All right. So there's formic acid. So why don't you try some here? Why don't you give the name of this one? Why don't we do? Okay, let's take a look and see. We'll start with the original one here. So first off, you hopefully should be able to recognize the carboxylic acid group. Again, that is our oxygen carbon attached to an OH group. So that is our carboxylic acid group there. And we just need to count up some carbons. So that is a carbon there. That's 2, that's 3, that's 4, and that is 5. I think that's going to be your longest because, again, if we went this way, 1, 2, and down would be 3, which obviously would be less. So it looks like 5 is our longest carbon chain that obviously has carboxylic acid group. So that's going to be pentanoic acid. Once again, not part of the longest carbon chain. That is a group in this case, would be just our lonely methyl group hanging off right about here. And we don't need to give the location of this group, but it definitely is going to be carbon number 1, which means this would be carbon number 2. And that would get us our 2-methyl pentanoic acid. Any questions on that there? All right, taking a look at our next one. I went backwards here. I put my carboxylic acid group over there. It doesn't really matter. Should be at one end or the other. So again, counting up our carbons here, looks like 1, 2, 3, 4. We could also go 1, 2, 3, 4. So we could technically kind of go upwards as well. We'll just take this straight one here. So go that way, I think. And if I do that there, I will end up with 1, 2, 3, 4. So that's going to be butanoic acid. This should be carbon number 1, carbon number 2, carbon number 3, where I have a methyl group hanging out. And that would then be carbon number 4, which would be where my bromol group would be. Again, we're going to go alphabetical like normal. So this will be something maybe like 4 bromol. We got there 3 methyl, looks like. And a little butanoic acid in this case. Questions on that one there? All right, lastly here, I see a benzene ring that has our carboxylic acid kind of hanging off of it. So that's going to be benzoic acid because that's a benzene ring. Once again, the carbon on the benzene ring where our functional group is attached is going to be carbon number 1. And again, because it does have the 3 double bonds, you could really go clockwise or counterclockwise to give the group the smaller number. So we will go this way to give it 2. And this looks like then a 2-chloral benzoic acid. Yeah. Any questions on that one there? why don't you try these here? Why don't you also maybe let's draw a couple here. Let's draw um let's draw 2,3 dichloral hexanoic acid. Okay, let's take a look. We'll start with A. So once again, we see our carboxylic acid group here. So we'll count up some carbons. Looks like 1, 2, and 3. Once again, we could also get 3 if we went upwards. So I'm just going to take the straight 3 here. So 3 would be based off of propane. So then this would become propanoic acid. Once again, this is definitely going to be carbon number 1 where the group's at. That would be carbon number 2, and that would be our location of the only group that's attached here, which is a methyl. So this would be a 2-methyl propanoic acid. Any questions on that one there? Once again, hopefully we can see our benzene ring with the carboxylic acid. So that's all kind of together. So that's going to give us our benzoic acid. And as we mentioned before, wherever this sort of carboxylic acid group's attached to the ring, that carbon in that ring will be carbon number 1. And once again, at this point, we do want to give the group the smaller number. So you could probably see if you go clockwise here, you will end up with a 3. Rather than counterclockwise, you'll end up with a larger number. So that's going to be 3-bromyl benzoic acid. Any questions on those two? All right, so drawing is like normal. We're going to work backwards. So clearly I see oic acid, which should tell me it's a carboxylic acid. And kind of the hexane part of it tells me it's 6 carbons. So once again, just going to start with carbons. So 1, 2, 3, 4, 5. I'll put 1 back away. In this particular case, you could put the carboxylic acid group at either end since you're drawing it. So I'm going to put it at the right end. So that is where my carboxylic acid group is going to look like. And because I chose to put it over there on the right-hand side, that definitely for me will now be carbon number 1. If you put it on the left-hand side, then that would be carbon number 1 for you on the left-hand side. So it just depends whichever way you did it. Then this would be carbon number 2, which should have a chlorine group. And this would be carbon number 3, which should have a chlorine group. And now we're pretty much at a name like normal. So we're just going to add in the proper number of hydrogens. We'll need 1 there, a couple there, and 3 there. And once again, if you were doing more like line structure, same idea. Just start with the right number of carbons. So 1, 2, 3, 4, 5, and 6. Again, wherever you want to kind of put the carboxylic acid, you could do that. That would again be carbon number 1. So it'd have a chlorine there and a chlorine there. Then we would be done at that point, hopefully. Any questions on either of those there? All right, so I want you to draw that. We'll draw a couple more here. So let's do 3-methyl butanoic acid. And let's go 2-ethyl 3-methyl benzoic acid. Let's try that there. All right. Let's take a look. Once again, always going to start backwards in the name here. So the oic acid, once again, tells us carboxylic acid. And again, a 6-pack here. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. Again, you can put it on either side, so I will put it over here. And by doing so, that again is going to make that for me carbon number 1. So that'll take care of that. And then we're just going to go to carbon number 4, which then would be for me right about here. And that's going to have a chlorine. At this point, we're pretty much out of names, so just going to get carbon to 4 bonds. So 2 hydrogens there, 2 there, just 1 there, 2 there, and 3. And once again, if you're going to do sort of line structure here, same idea, 1, 2, 3, 4, 5, 6. I guess we'll go down this way then. OH, double bonded oxygen, going to be carbon number 1, 2, 3, and then this would be my 4 here. It'll look something like so. Yes. Questions on that there? All right, so oic acid, still carboxylic acid, butane, basically 4 carbons. So if we did more of a condensed formula, it looks something like this. Again, going to be carbon number 1. And for me, we'll go 3 down there. We'll put my methyl group, and that takes care of the whole name. And now we'll put our hydrogens in. So we got 2, 1, and 3. Once again, if you're doing more of a line structure, 1, 2, 3, 4. Once again, remember you got to kind of bring it down and attach the OH and make the double bond. Again, don't forget to put this stuff at the end, otherwise it is a carbon. And that would be carbon number 1 for me. So we're going to 3, 2, 3 would be something like that. Yeah. Any questions on that one there? And lastly, benzoic acid, definitely a benzene ring situation. And I'll just pop mine right off of here. And once again, you could put this carboxylic acid group off of any of those carbons, and wherever you put it, it would just be carbon number 1. So for me, since I did, that would be my carbon number 1. And really in this case, you could go left or right. It doesn't really matter. So I'm going to go right and just go 2, and that's going to be an ethyl group. And 1 more over would be 3, which would be a methyl group, looks something like so, yeah. And once again, if you decided you absolutely, in this case, because it's benzene, could have went that way and put the groups in that order on that side. It's basically just the same thing, just turned around, basically. Any questions on how to name, draw carboxylic acids? All right, so let's then talk about some of the properties here of carboxylic acids. As I mentioned before, they do contain 2 polar groups. When they do react, they sometimes will make what is sometimes referred to as a carboxylate salt or carboxylic acid salt. It's really, as we will see, just the kind of acid-base reaction that we talked about when we did the acid-base chapter, just involving a carboxylic acid. A lot of weak acids are carboxylic acids, things like acetic acid and so forth. So we see similar reactions that we saw previously. As I mentioned before, because it does have those 2 very polar groups, that plays a really big role, as I mentioned before, in terms of boiling points and melting points. It also plays a really big role in terms of solubility with things like water. And remember that water is a polar molecule. Also has obviously more positive on the hydrogens, more negative on the oxygens. So because these guys have basically those same groups, they can hydrogen bond really well with water. So again, we're going to see some good solubility of carboxylic acids in water. And again, like I mentioned before, because of those 2 groups, they definitely will have higher melting points and boiling points. They can form hydrogen bonds with lots of water molecules, does make them soluble. But pretty much like all organic molecules, even though they do have these 2 polar groups, if you increase that sort of non-polar side of the molecule, where it's just the carbons and the hydrogens, we do start to see really a decrease in the solubility, kind of like what we saw with alcohols as well. So again, a big theme in organic chemistry in terms of solubility is, and in ways things can interact with each other is, if sort of the organic guy is a little bit too big in the kind of non-polar part of the molecule, a lot of times that causes what's known as steric hindrance, and it just prevents things from getting into each other and working really well with each other. It just kind of gets in the way. Um, so with 1 to 5 carbons, your carboxylic acid is going to be fairly soluble. So upwards of pentanoic acid, you should have some solubility in water. Again, once you get above that, hexanoic acid and so forth, it's just that nonpolar part's going to get too big to really be helpful. As we can see here, pretty soluble down to 5, and then we're getting into slightly soluble and really insoluble after that, which is pretty much what slightly soluble means. They are typically, as I mentioned, weak acids, and they can ionize in water, and they can break apart like any type of acid in water, and it basically will break apart into H plus and the acid. So it will do its ionization. This is acetic acid, which is ethanoic acid. And basically what it's going to do, if you show the water here, it is a weak acid. And we're just going to do our Bronsted-Lowry definition here. So this is an acid, which means it's going to send that H plus. And by the way, that is the H plus that's going over. Always offer the oxygen is pretty much what makes that part of it the acid. And it's going to send over there, and is going to make our carboxylic salt here, our ion, and our H3O plus, which is hydronium ion. And that is obviously going to make it an acid type of solution. This is the same thing, again, as we saw in the acid base chapter, where maybe we didn't react it with water and we just showed it breaking apart into acetate and H plus. So it's the same sort of idea as what we talked about there. So they typically can make a carboxylate ion, and that is basically acetate here, which is basically what that guy is. And again, kind of a weak acid and its conjugate base pair there basically is what we're looking at in that situation. Also makes a nice buffer, those two things. So if we take a look at butanoic acid dissociating in water, again, we will start with butanoic acid, which tells us it is 4 carbons. So 1, 2, 3, and 4. And we'll put in our hydrogens there. Not too many, maybe. There we go. And again, dissociating in water is just going to be our H2O here. And just going to be our acid sort of base reaction. It's going to send this H plus over. And nothing's going to change other than we're going to take that positive guy off. So as we kind of saw when we were doing the alcohol to our aldehydes and ketones, when that alcohol kind of loses the H, what's left, it becomes negative because you remove a positive. So you become more negative here. And we will end up with again, a negative charge at the end here. And that will be balanced out by the H3O plus, which again would make this a acidic solution here of this acid. So carboxylic acid, which is your probably majority of your kind of weak acids, definitely could do all the same sort of acid-base reactions that we saw in the acid-base chapter. Any questions on that there? All right, if you want to take a break for 5 minutes, come on back and we'll. Okay, we're going to continue on. So we have our acid that can dissociate in water, like any type of acid, as we talked about. This carboxylate ion that it forms, you will not be responsible for like naming it or anything or giving the name of it. But as you can see up here, you kind of just put O8 on it. So that would be butanoate ion, but you're not going to be responsible to name it. But that's just what it's formed. Now, because it obviously is an acid, in addition to just kind of dissociating or breaking apart in water, it could do just a regular old acid-base reaction like we saw in chapter 10 or whatever chapter that was. And obviously here our methanoic acid, here our formic acid is going to be our acid. Our sodium hydroxide is going to be our base. So this is the same reaction we sort of saw in that chapter. If you remember, when you take an acid plus a base, you will form two things. You will form a salt and water. And that's the same idea what you form here. Just like when we talked about those reactions in that chapter, pretty much the H comes from the acid, the OH comes from the base, and that again is how we get our water, basically, is what happens. It is that double displacement reaction that's occurring. And then basically what is left over will make our salt. So this is our salt here, and that is going to be just an ionic compound. The sodium is just hanging out basically to balance out the charge. But when this guy goes off, this guy then becomes negative, which is what we see over here. And we get a salt here and obviously water that is formed in this case. So this is still really our double displacement reaction that we talked about in that chapter. Just switching partners, as this is, we just wrote it sort of in formula form here. Over CH, right, in this case, and plus our sodium hydroxide. So this is our positive negative guy, and we're just switching partners here, just like we did before, basically to make water. So if we take a look at this here, which is our benzoic acid, once again, this is our acid, this is our base. This is basically our negative guy to the left, and our hydrogen is positive. This is our positive, this is our negative. And once again, here it's going to be the H from the acid and the OH from the base. That's going to make our water. And then basically this is what's left over is going to be our salt in this case. And nothing really changes on the guy on the left there, other than he now has a negative charge, as you can see in the picture there. And that negative charge is going to be balanced out by the positive charge here, and that is again going to be our salt that is formed in this particular case. So carboxylic acids, because they are acids, they basically could just do an acid-base reaction, just like we saw there in that previous chapter. Any questions on that there? Yeah. Correct. So basically this entire thing, if you will, this entire thing has a -1 charge. Yeah. And these guys aren't bonded together through sharing of electrons or anything. This is just that ionic interaction of opposites attract to each other. So the potassium here is what's known as a spectator ion. It's just there floating around the solution. It's not really doing anything, just kind of floating around to balance out the charge of the solution. And it's still really, this is your acid, and this is really its conjugate base, just like we talked about in that acid base chapter. If you just look at this, the only difference between these two guys is that Bronsted-Lowry difference we talked about, which is 1H plus difference is the only thing between those guys. Other questions on that? All right, so carboxylic acids are ionic compounds with strong attractive forces. They are solids at room temperatures. They typically have high boiling points and melting points, and usually are soluble in water because they are salts, so they're ions, so they work well in water. They can get surrounded by water and work really well. So a lot of carboxylic acid salts are used as preservatives and flavor enhancers, like all those weird things you see on labels, like sodium propanoate, sodium benzoate, MSG, monosodium glutamate. Again, these are all salts that have certain properties that can be helpful and not so helpful. So if we're going to write our balanced chemical reaction here, once again, we're going to start with our propanoic acid, which should be 3 carbons, 1, 2, and 3. And again, you could put the OH on either side you like. We're going to react it with sodium hydroxide. So once again, that is a carboxylic acid. That definitely is a strong base. So you just want to think about your acid-base reaction. So once again, here we should form water. And as we've been seeing and been talking about, always going to form from those two parts, basically. So that's always where our water is going to come from. Pop water in there. And then obviously we're just going to kind of draw this entire thing exactly the way it is, except now it's going to be negatively charged on the other side. So this is going to make the salt part that's left over. And once again, it shouldn't get all fancy with it, right? So it's just going to do that. And the only other thing that's left is a sodium ion that's floating around. And that's really our double displacement move there. So that's going to give us our salt here. And then obviously we get our water in this case. So it is the exact same reaction as the acid-base one. The only difference is here, we're just drawing the structures rather than just using the formulas like we did in sort of that chapter there. So it's just kind of the same idea in this case. It's still, once again, a double displacement reaction. This guy switches partners with the sodium, and obviously the two green guys come together here to make what's on the other side. So it's just that double displacement reaction we talked about a lot throughout the chapters. Any questions on that reaction there? All right. All right, the next sort of functional group we're going to talk about are esters. And esters are pretty much a combination of a carboxylic acid and like an alcohol coming together. So it has a functional group of carbon, oxygen, double bond, oxygen to carbon, so not to hydrogen. And this is our ester functional group. And it is resulting from, as I mentioned, really carboxylic acid and an alcohol coming together to make that bond. And as we'll talk about, that's sort of how we end up with this functional group here. So unlike a carboxylic acid, it doesn't have that OH group at the end. So it's not as polar as a carboxylic acid would be because it is missing that. A lot of esters are basically a result of a lot of sort of smells and flavors that we associate things with. And we can synthesize it from a reaction of a carboxylic acid and alcohol. And that is this reaction here. So we would have a carboxylic acid. And we react it with an alcohol. And I'm just going to kind of turn my alcohol around here. We'll just do a very simple one here. And essentially what happens is you basically just add them together. And what's going to come out of this reaction is water. And however you want to kind of think about the water as to how it gets there. But basically we're going to take water out here. So I'm just going to highlight here. A couple H's and an oxygen are going to go out. And basically just kind of squeeze everybody else together. Go to the left, go to the right there. And obviously just take the water out of it. So we will end up with CH3, C double bond O, O. Once again, nothing here changes. Obviously, that is what makes water. So what I'm left with is just a CH3 on the back end of it. And that is what's going to make our ester here. And once again, you can kind of see the functional group here of the ester, carbon, oxygen, double bond, and oxygen, carbon here for our ester group. This is what is referred to as an esterification reaction. Basically how you make an ester. This is basically how you make an ester. Carboxylic acid and alcohol come together. You dehydrate it, take the water out, everybody gets squished together, and you form your ester here. Uh, again, like I said before, they're responsible for a lot of aroma and flavors, like things like bananas, oranges, strawberries are different types of esters that come together. This is also a good way to kind of think about kind of how to arrange this is just kind of back up those kind of functional groups to each other. So you could just take the water out and squish everybody together. So once again, here our esterification reaction. We're going to take out our water and basically just squash them together there. And we will end up with our ester on the other side there. And really, in this case, how we name it is all based on sort of where this functional group is and sort of what came from what here. So if we take a look at this ester here that is formed as a result of what we're looking at the bottom there. So it is definitely going to come together always between the carbon and the oxygen there, that single bonded carbon and oxygen, not the double bonded. So that's always how they come together. Now, as you go towards the double bonded oxygen, that's your carboxylic acid part of your ester. And as you go away from that carbon oxygen double bond, that is your alcohol part. So we really have these two parts to an ester, and that's important for basically our name and how we name it. So the alcohol part is named as like a group name. So for example, here, if we look at the alcohol part, which is over here on the right, the only carbon we have is one carbon, and we would call one carbon group a methyl group, right? So that is a methyl group. Now, if we go to sort of the carboxylic acid side, that has two carbons, which is an ethyl group, or basically based off of ethane. And we do drop the E off of the ethane and put OATE at the end. So O8. And then we basically just put those together, group first. So this is methyl for the alcohol or the smaller part, and ethanoate for our carboxylic acid part. We don't have to give the location of where the carbon oxygen double bond is. Again, you just got to sort of be able to identify when you look at one, sort of which part came from which. So you always want to think about breaking it apart at that carbon oxygen bond. And again, if you go towards the carbon oxygen double bond, that's always the carboxylic acid part because that's where that comes from. And the other part should be the alcohol part. So kind of the single bonded oxygen there should always be the alcohol part, kind of going away from the double bonded oxygen. Any questions on that there? So here's another example of an esterification reaction. We're going to take ethanoic acid and 1-propanol. Once again, all we're going to do is, and if you had to draw these and they weren't kind of lined up like this, it's probably, like I said, a really good idea just to kind of turn maybe your alcohol around so that the OH of the carboxylic acid and the HO of the alcohol are lined up, because then basically all you have to do is just put a box around water and then just squish everybody else together. And that's just a good way to kind of visually see it. And you just take your water out, and then all you have to do is just start drawing from there and end up on this side. So you just put it together. And you will get it kind of put here. This, by the way, would be if we were going to name it like we see on the bottom. As I mentioned before, we're going to kind of break it apart here. And towards the double bonded side is the base of the name, the carboxylic acid part. And that is also two carbons. So that is ethanoate. Going the other way away from the double bond is from the alcohol, and that's just named as a group. And there is 3 carbon group there. So this is known as propyl ethanoate. So the carboxylic acid part of the ester is the base of the name. The alcohol part is named as a group and comes in front, obviously, as well. If you're going to do a little line sort of structure here, I would probably start almost like we do ethers with the oxygen in the middle. And, to the right there, in this case, we have 3 carbons. So 1, 2, and 3. And to the left there, we have our carbon oxygen double bond, just 2 though. So 1, 2, and then we're gonna go here, and that'll be it in that case. Yeah. So it looks something like that. Just kind of build it from the oxygen out. So if you're going to draw these, start with the oxygen, kind of build each side of it. Very similar to what we talked about when we did kind of ethers, is a good way to kind of do that. Even if you're doing condensed structure, same idea. I would just start with the oxygen, go, okay, I got like propyl over here, so that's 3 carbons. I got 2 carbons on this side. And then again, you could just kind of fill in your hydrogens and get your compound there. If we're doing more of a condensed structure type of deal. Something like that. All right, so why don't you try it here? Write the balance equation. If you take propanoic acid and methanol, let's see what you get. Okay, so let's take a look, see how you're doing. We'll start with our propanoic acid, which obviously is our carboxylic acid. And that means propane, which is 3 carbons. We'll put my OH group on that side just to kind of line it up nicely. Methanol should be just 1 carbon, so it should look something like this. And once again, I'm just going to kind of line those things up, so just make it easier to draw my final product. And when these 2 guys come together, we should always know we're just going to take water out. So you could, again, just kind of box it, highlight it. And obviously that's going to come out as water here. So we'll do that there. And really at this point, since we lined it up nicely, we just need to start left to right there and just put everybody together, take the water out, obviously. And I'll just go underneath here so I don't run out of room. CH3, CH2, C double bond O. Once again, we're taking this out, so we're not going to do it. That's going to give us our ester connection here to our 1 carbon group on that side there. Any questions on that one there? Can you write what now? Oh, you could go across. I just ran out of room. It doesn't really matter. I just kind of ran out of room, so I went down. So that's a squish it in there. As long as on the right hand side of the arrow, that should be okay. If we were going to name this, once again, we would be looking here. And again, towards the double bond is our carboxylic acid part. Away from it is our alcohol part, right? So that's our carboxylic acid. And it is the carboxylic acid that is the main part of the name. So it's got, as we can see here, 1, 2, 3 from propane. So that's going to be propanoate. And on the alcohol side, we have just 1 carbon. So we just made methyl propanoate in this case. Questions on that there? And again, this is what is known as an esterification reaction. It basically is how you make a ester, in this case, carboxylic acid plus an alcohol. Get you your ester. Yeah. I don't know if you'll need to name it as an esterification reaction. It may be mentioned in a problem or something. So you probably should have an idea of what it means. But you will need to be able to obviously identify all those kind of functional groups in this reaction for sure. Yeah. That is an ester, yeah. So, and that's the ester connection where those two guys come together. And the ester functional group is the carbon oxygen double bond to an oxygen that's really attached to a carbon. And again, the hydrogen comes off obviously in this process. So that's where we lose that H on that carboxylic acid as it makes water. Other questions? Uh yeah, you could do 2 words on it. It's okay. Yeah. I'll take either one. It's fine. All right, there. So here is our naming here. And again, that's really what you want to kind of think about in this case is our kind of 2 parts. So always just focus on where I know they kind of box it a little differently. I would always just kind of focus on between that single bonded oxygen, and that will usually kind of go away from the double bond or towards a double bond to give you your 2 groups in terms of your name. Right. Esters do have common names. We're not going to use really too much of the common names. For example, ethyl ethanoate is ethyl acetate. Methylpropanoate is methylpropanoate, which sounds very similar. This is ethyl benzoate. Here again, we have our benzoic acid there. Salicylic acid is a ester, and again, it is major component there in aspirin. You can kind of form aspirin, form it. This is a carboxylic acid. Obviously, we have 2 carboxylic acids, also have an alcohol down here. And these guys are going to come together here just through our esterification reaction to make our ester, our carbon, oxygen, oxygen, carbon bond there. So there's our ester group right there, which is really the main component there in aspirin. Same idea here. We have our carboxylic acid group here and our alcohol coming together to make oil of wintergreen here. All right, so why don't you name this ester? Why don't you draw? Let's do ethyl pentanoate. Let's do methyl. Really our ester group right around here. So if we could see that. Again, probably the easiest approach is just to go, okay, I'm just going to kind of break it apart right about there. And remember that if we go towards the carbon-oxygen double bond, that's our carboxylic acid part that has the carbon-oxygen double bond in it. If we go away from it, that's your alcohol part. So once again, it is, again, the carboxylic acid part. That's the main part of the name. So we'll just count some carbons, 1, 2, and 3. So that's going to be propanoate. And got a 2 carbon group there on the alcohol part, which will be an ethyl. So again, here we get an ethyl propanoate in that case. Yeah. Any questions on that one there? All right, so we're gonna draw it, and here obviously the O8 is a key to hopefully that you recognize is a ester. So again, that's why we want to do that. So if I was going to draw these, again, I would probably take kind of like the ether approach and stuff like that. Since I know that this is the connection, I would actually just start with that part. And really, if you do that, all you have to do is put the proper number of carbons on either side here. And I do know that the carboxylic acid side should have 5 carbons, and that should be the side that has a double bond on it. I do need to be careful here because I already have 1 carbon written, right? So I actually just need to add 4 more to get me 5 on that side because we do need to include that carbon in our counting there. So 1, 2, 3, 4, and 5. That will give us our 5. And ethyl is the alcohol side, which would be 2 carbons. And now, just like normal, we're just going to put in our hydrogens here to get everybody to 4. So we'll go 3 there, 2 there, none there, 2 there, 2, 2, and 3. Now, if I was going to do maybe something like a line structure, I would probably still approach it pretty similar here. And that would kind of give me something like so. Um, in this case, though, I would just need to go to here. And since I drew it like this, I actually have two to start with here. So again, I would just need to add in three. So 1, 2, and 3 there. And that should give me my ester in that case. Yeah. So sometimes it might be easier just to start in the middle, kind of just put the carbons on either side of it. And just might be an easier move. Any questions on that there? All right, so taking a look at this one, O8 tells me it's an ester. Benzene kind of tells me it's a benzene ring. So I definitely got myself a benzene ring happening here. And remember that it's really based off the carboxylic acid, which comes off of the benzene ring, right? So again, that carboxylic acid part's off the benzene ring. And methyl would mean I just have one more carbon, which I did all the line structure, looks something like that. Or you could obviously, maybe not for the benzene ring, but you could do a little bit of this. Do something like that as well. Yeah. So that is an important thing. Just remember again that the benzoic acid has the carboxylic acid as kind of like an attachment to that ring, and you don't want to try to incorporate it into the ring or anything like that. And that means that the ester here will also have a similar type of incorporation of that group on the outside there of the ring. Any questions on any of those there? All right, I think we'll lay it up there for today, I think.